Have you ever looked up at the stars on a clear night and felt that profound sense of wonder, that humbling feeling of being part of something so much larger than ourselves? That quiet awe is just the beginning. Out there, in the immense stretches between the stars, the universe is hiding secrets that defy everything we think we know. Astronomers are regularly left speechless by events that simply should not be possible: bursts of energy brighter than galaxies appearing out of nowhere, invisible matter sculpting the cosmos, and forces acting in ways that break the very rules of physics. These aren't just curiosities, they are cosmic puzzles that challenge our understanding of reality itself. Today, we're setting out on a journey to explore 21 of the most bewildering, breathtaking, and downright impossible phenomena occurring in interstellar space. From mysterious fast radio bursts that flash for just milliseconds yet carry more energy than our sun emits in days, to rogue planets drifting alone through the darkness, each of these discoveries pulls back another layer of the universe's deepest mysteries. We'll dive into gravitational anomalies that make no sense, particles that arrive with impossible energy, and structures in space so vast they challenge the fundamental principles of cosmology. This isn't science fiction, it's what's happening right now in the silent expanse above us. By the end of this video, you won't just have a list of strange space facts. You'll see the cosmos in a new light, not as a static, predictable backdrop, but as a living, evolving frontier full of surprises waiting to be decoded. Each of these 21 phenomena raises more questions than it answers, inviting us to rethink what is possible and urging humanity to look deeper, question further, and imagine bigger. So settle in, open your mind, and get ready to explore the impossible. The universe has been keeping secrets, and it's time we uncovered them together. But to truly appreciate these cosmic oddities, we first need to understand the stage on which they perform. We often picture the space between stars as a perfect, silent void, an endless black emptiness. That picture is completely wrong. Interstellar space is not empty at all. It is a dynamic, seething ocean of incredibly sparse but fascinating activity. This environment is filled with wispy clouds of gas, primarily hydrogen, and fine dust grains thinner than any smoke. It's crisscrossed by powerful magnetic fields and flooded with various forms of radiation, from starlight to cosmic rays. This is a realm where conditions are so extreme and unfamiliar that they create a natural laboratory for physics we can scarcely replicate on Earth. Here, the rules seem to bend. The vacuum itself is alive with quantum foam, a conceptual sea of virtual particles flickering in and out of existence. Dark matter, whatever it is, weaves its invisible gravitational web through it all, dictating the motion of galaxies while remaining utterly undetectable to our eyes and instruments. To even begin to explain the strange events that occur in this medium, scientists must constantly return to our most fundamental theories: Einstein's theory of general relativity and the bizarre laws of quantum mechanics. And yet, time and again, these powerful frameworks fall short. They provide the map, but the territory keeps revealing new, uncharted features. History is littered with these moments of beautiful confusion. Take the Pioneer Anomaly, for instance. For decades, scientists were utterly baffled by the tiny, unexplained deceleration acting on the Pioneer 10 and 11 spacecraft as they traveled into deep space. Or consider the famous WOW signal, a powerful 72-second burst of radio waves detected in 1977 that seemed to scream of an intelligent origin, yet was never heard again. Each of these puzzles, from the minute to the monumental, has forced a profound re-evaluation of our cosmic models. They are not mere footnotes in astronomy textbooks. They are glaring signposts pointing toward gaps in our understanding. This background is crucial because it frames our entire journey. The 21 phenomena we're about to explore are far more than just a list of interesting space facts. They are the keys. Each one is a potential lock that, when unlocked, could open a door to an entirely new branch of physics, a deeper comprehension of the cosmos, and a more profound answer to the question of our place within it. So as we venture deeper into this catalogue of the impossible, remember that every mystery is not a dead end, but an invitation, a direct challenge from the universe itself to look closer, think deeper, and explore further. Picture a burst of radio energy so powerful it outshines entire galaxies, lasting just milliseconds yet traveling billions of light years. This is an FRB. First detected in 2007, these enigmatic signals originate from deep space, with some repeating unpredictably while others occur once and vanish. Theories range from neutron star collisions to alien megastructures, but no explanation fully accounts for their immense energy and brevity. For instance, FRB 121102 repeats periodically, suggesting a rotating source like a magnetar, yet its energy output defies known stellar processes. What makes FRBs so perplexing is their ability to propagate through space without significant dispersion, hinting at unknown interstellar mediums or new physics. Could these bursts be natural cosmic lighthouses or something more artificial? As we ponder this, let's turn to another head-scratcher: dark matter's ghostly influence. Now shift your focus from those brilliant, fleeting flashes of energy to something far more pervasive and profoundly invisible. Imagine the universe's hidden architecture, an invisible scaffold, a cosmic skeleton that holds galaxies together and dictates the large-scale structure of everything we see, yet it emits no light, no energy, and refuses to interact with ordinary matter in any way we can easily detect. This is the enigma of dark matter, a substance that makes up roughly 27% of the entire cosmos, far outweighing all the stars, planets, and gas clouds combined. For decades, our best computer simulations of the universe, based on the known laws of gravity, have made a very specific prediction. They show that this dark matter should clump together, forming dense halos around galaxies and even tighter subhalos within them, with vast, empty voids in between. This isn't a minor detail. It's the fundamental expectation for how cold, collisionless particles should behave under gravity's relentless pull. But the universe, in its classic fashion, loves to defy expectations. When astronomers meticulously map the actual distribution of dark matter out in the interstellar voids, using ingenious techniques like gravitational lensing, where they observe how the dark matter's gravity bends the light from distant galaxies, they find something startling. In many regions, especially within the immense and lonely cosmic voids, the dark matter is far smoother, far more evenly distributed than any simulation predicted. It's as if we expected to find a range of sharp, jagged mountains and deep valleys, but instead we're looking out over a landscape of gently rolling hills. This isn't just a small miscalculation, it's a direct contradiction that strikes at the heart of our gravitational models. One of the most compelling pieces of evidence for dark matter's existence actually highlights this very puzzle. Consider the famous Bullet Cluster, a spectacular collision of two galaxy clusters. During this cosmic crash, the clouds of visible gas, which do interact and slow each other down, got stuck in the middle. But the dark matter, inferred from its gravitational lensing effect, sailed right through the collision, completely separate from the gas. This proved decisively that dark matter exists and that it doesn't interact with itself or with normal matter through any force other than gravity. Yet this same ghostly nature is what makes its unexpected smoothness so baffling. If dark matter particles truly don't bump into each other, what stopped them from collapsing into the dense clumps our models require? It's a paradox that has cosmologists scratching their heads. This entire quest began with the groundbreaking work of astronomers like Vera Rubin in the 1970s. By meticulously measuring the rotation speeds of stars within spiral galaxies, she discovered that stars at the outer edges were moving just as fast as those near the center. According to Newton's laws, these outer stars should have been slowing down, destined to fly off into space unless some unseen mass was providing extra gravitational glue. That invisible mass was dark matter. Her work provided the first major clue to its presence, but decades later, its fundamental nature remains the biggest unsolved mystery in physics. We've built incredibly sensitive detectors deep underground, shielded from cosmic rays, hoping to catch a single, fleeting interaction of a dark matter particle, and yet we have never directly detected one. This glaring discrepancy between what we expect and what we observe forces us to confront two equally radical possibilities. Either our understanding of gravity itself is incomplete or flawed on the largest scales, requiring a major revision of the laws laid down by Newton and Einstein, or dark matter possesses unknown, complex properties that our simple models of weakly interacting particles have failed to capture. Perhaps dark matter particles can interact with each other through some unknown dark force, or maybe they have a tiny intrinsic velocity that prevents them from clumping as densely as we thought. Each option would revolutionize physics. The smooth, ghostly distribution of dark matter in the voids of space is not a minor detail. It's a profound clue whispered from the darkness, urging us to look deeper and question our most basic assumptions about how the universe holds itself together. Now let's journey from the vast, invisible scaffolding of dark matter to a mystery that hit much closer to home, or at least within our own solar system. It's a tale of two intrepid robotic explorers and a tiny, persistent nudge that defied explanation for decades. In the 1970s, NASA launched the Pioneer 10 and Pioneer 11 spacecraft on grand tours to the outer planets and beyond. These pioneers were the first to venture through the asteroid belt, the first to make close observations of Jupiter and Saturn, and the first human-made objects set on a trajectory to leave our solar system entirely. As they sailed into the deep black, engineers back on Earth meticulously tracked their positions using the Doppler effect, monitoring the subtle shifts in their radio signals to calculate their velocity and trajectory with incredible precision. For years, everything proceeded exactly as Newton and Einstein would have predicted, but then something peculiar emerged from the data, an incredibly slight but undeniable anomaly. Both spacecraft were experiencing a minute, unexpected acceleration back toward the Sun. It was vanishingly small, roughly 874 billionths of a meter per second squared. To put that almost imperceptible force into perspective, it's equivalent to the gravitational pull you'd feel from a single grain of sand held in your hand from a mile away. For the Pioneer craft, this tiny tug meant they were about 250,000 miles off from their predicted positions after a decade of travel. While that sounds like a vast distance in the grand scale of the solar system, it's a minuscule error, but for physicists, an error is a clue, and an unexplained error is a potential revolution. The immediate reaction was to look for a conventional explanation. Was it the pressure of solar radiation? Calculations showed that was far too weak. Could it be the gravitational pull of undiscovered objects, like a hidden planet or a ring of dust? Searches turned up nothing. Perhaps it was an effect of the spacecraft's own fuel leaks or outgassing. Again, the numbers didn't add up. The most widely accepted explanation, after years of painstaking analysis, pointed to an asymmetric heat radiation. The idea was that electricity generated by the probe's plutonium-powered radioisotope thermoelectric generators produced heat, which was then radiated away from the spacecraft. If slightly more heat was radiated from one side of the craft than the other, it could create a tiny thrust like a very faint photon rocket. This seemed to solve the puzzle for many, but a stubborn group of scientists remained unconvinced. Their biggest counter-argument came from another set of famous travelers, the Voyager probes. The Voyager spacecraft, which followed similar paths into interstellar space, did not show the same anomaly, at least not to the same definitive degree. If the Pioneer Anomaly was caused by a simple design flaw like heat radiation, why wouldn't the Voyagers, with their different designs and navigation systems, exhibit a similar deviation? This inconsistency kept the door wide open for far more exciting, if speculative, theories. Some physicists proposed that this constant sunward acceleration might be a sign of a need to modify our laws of gravity itself, perhaps an extension of theories like MUN that we encountered with galactic rotations. Others wondered if it could be an effect of dark matter interacting with the spacecraft in a way we hadn't predicted, a local cloud of exotic particles exerting a drag. The most mind-bending suggestions even ventured into the realm of how gravity might behave differently at extremely low accelerations or over vast distances. The Pioneer Anomaly became a classic example of how the most precise measurements can reveal the most profound gaps in our knowledge. It demonstrated that even a force 10 billion times weaker than Earth's gravity could not be ignored if it didn't have an explanation. It was a humbling reminder that our understanding of the fundamental forces, even within our own cosmic neighborhood, might still be incomplete. While the thermal explanation is now the leading theory, the debate itself underscores a critical principle in science. Sometimes the smallest, quietest signals point toward the biggest questions. After contemplating the subtle, unexplained forces acting on our spacecraft, we now venture into a realm where the very fabric of reality itself seems to fray at the edges. We are about to explore the most fundamental and perhaps the most baffling of all these cosmic puzzles, one that arises not from distant galaxies or massive objects, but from the nature of empty space itself. The central idea here is so counterintuitive it almost sounds like magic. A perfect vacuum, the complete and total absence of all matter, is not empty. According to the fundamental principles of quantum mechanics, what we call empty space is in fact a seething, bubbling, frenetic sea of activity. At the tiniest imaginable scales, pairs of virtual particles and their antiparticles are constantly flickering into existence, borrowing energy from the universe for an infinitesimally brief moment before annihilating each other and vanishing back into nothingness. This ceaseless, chaotic dance is known as quantum vacuum fluctuation, and the energy it represents is called vacuum energy. This isn't just a wild, theoretical concept. We can actually observe its effects in the laboratory. The most famous demonstration is the Casimir effect. When two incredibly smooth, neutral metal plates are placed extremely close together in a vacuum, they are gently pushed toward each other by an invisible force. Why? Because the tiny gap between the plates is so small that only certain wavelengths of virtual particles can pop into existence there. Outside the plates, a wider variety of particles can flicker in and out. This difference in quantum activity outside versus inside the gap creates a subtle pressure that nudges the plates together. It's a real, measurable force generated by the energy of seemingly nothing at all. Now, if we scale this phenomenon up from a lab experiment to the entire cosmos, we run into what many physicists consider the most embarrassing and profound problem in all of theoretical physics. the cosmological constant problem. The calculations are startling. When you add up the potential energy from all these quantum fluctuations happening everywhere in the universe, across all of interstellar space, the result is a number so astronomically huge it's almost meaningless. This vacuum energy should act as a powerful repulsive force, causing the universe to expand at a rate that would tear absolutely everything apart almost instantly. Stars, planets, and even atoms could not hold together against this incredible inflationary pressure. And yet, when we look out at the actual universe, we see something completely different. The expansion is happening, but it's far, far slower and gentler. The observed value of this vacuum energy, often called dark energy, is about 120 orders of magnitude. That's a 1 with 120 zeros after it, weaker than what quantum theory predicts. It is the worst mismatch between prediction and observation in the entire history of science. This isn't a small rounding error. It's a screaming contradiction that points to a fundamental gap in our understanding. Either our theory of quantum mechanics is profoundly incomplete when applied to the scale of the entire cosmos, or there is some unknown, cancelling mechanism at work that almost perfectly neutralizes this vacuum energy, leaving behind just the tiny trickle we observe as dark energy. Some theorists propose a kind of cosmic fine-tuning, where an unknown field or principle acts to suppress the vacuum energy. Others suggest this might be a clue that we need an entirely new theory that can successfully marry quantum mechanics with gravity, a theory of quantum gravity that would rewrite the rules for the vacuum itself. The sheer magnitude of this discrepancy tells us that we are missing something absolutely monumental. The apparent nothingness of interstellar space is, in fact, the most active and energetic thing imaginable, and its secret workings hold the key to understanding why our universe is structured the way it is, and perhaps even why it can support life at all. This profound quantum mystery, hidden in the void, sets the stage for our next phenomenon, where particles themselves defy the very limits we thought were absolute. If the idea of empty space bubbling with quantum energy stretches your imagination, then prepare for a phenomenon that seems to defy the very laws of physics on a cosmic scale. We are now entering the realm of the universe's most extreme and violent particle accelerators, far beyond anything we can build on Earth. Imagine a single subatomic particle, a proton or the nucleus of an atom hurtling through the void with unimaginable force. This isn't just a fast-moving particle. It is a bullet of pure energy, carrying with it the kinetic energy of a professionally pitched baseball, all compressed into a speck smaller than an atom. These are ultra-high-energy cosmic rays, and according to everything we know, they simply should not be able to reach us. The reason for their impossibility lies in a cosmic barrier known as the Greisen-Zatsepin-Kuzmin, or GZK Cutoff. Our universe is not a perfect vacuum. It is filled with the faint, cold afterglow of the Big Bang, the cosmic microwave background radiation. This sea of ancient photons is incredibly sparse, but for a proton traveling at nearly the speed of light, this background radiation is as thick as fog. According to well-established physics, a proton with energy above this GZK limit should violently collide with these background photons within a relatively short distance, losing its immense energy long before it could ever hope to cross the vast interstellar and intergalactic distances to reach our detectors. It's like trying to sprint through a dense forest. Eventually, you'll collide with a tree. These particles should be stopped in their tracks after traveling only about 150 million light-years. And yet they arrive. We know they arrive because of extraordinary facilities like the Pierre Auger Observatory in Argentina, a detector the size of a small country. It doesn't catch the particles directly. Instead, it watches for the massive showers of secondary particles they create when they slam into the top of our atmosphere. The data from these observatories is unequivocal. These cosmic cannonballs are real. The most famous example is the so-called "Oh my God" particle, detected over Utah in 1991. This single proton possessed an energy of about 300 exaelectronvolts. To grasp that, it had the kinetic energy of a baseball moving at nearly 100 kilometers per hour, all packed into a single fundamental particle. It was moving at 99.9999999999996% of the speed of light, so close to the ultimate speed limit that in a race with a photon of light traveling from a distant star to Earth, it would lose by less than a fraction of a millimeter. The mystery deepens when we try to trace these particles back to their source. When astronomers point their telescopes in the direction from which these ultra-high-energy cosmic rays came, they often find nothing. Empty interstellar space, no nearby active galaxy, no brilliant quasar, no violent supernova remnant. It's as if a cannonball flew across a battlefield with no cannon in sight. This makes the acceleration mechanism the central puzzle. What natural force in the universe can possibly act as a particle accelerator so powerful that it can impart millions of times more energy than the Large Hadron Collider? Theorists have proposed some incredible engines, perhaps the spinning, magnetic hearts of nearby pulsars, or the unimaginable shockwaves from merging galaxy clusters. Some have even suggested the decay or annihilation of hypothetical super-heavy dark matter particles lurking in the halos of galaxies, but each of these ideas faces significant challenges. The distances involved are often too great to overcome the GZK cutoff, and the required energy output pushes the limits of what we believe even the most powerful astrophysical objects are capable of. The existence of these particles therefore hints at one of two revolutionary possibilities. Either there are incredibly powerful, yet entirely unknown and invisible astrophysical engines lurking in the void, capable of launching these particles across the universe, or our understanding of particle physics itself is flawed. Perhaps at these extreme energies, the laws that govern how particles interact with the cosmic microwave background are different, maybe due to effects predicted by theories of quantum gravity that we have yet to discover. These cosmic rays are more than just high-energy particles. They are messengers from the most violent corners of the cosmos, carrying with them secrets that challenge our perception of reality itself, forcing us to question the very rules of the game. Now, let's shift our perspective from the tiny, high-energy messengers of the cosmos to the grand, sweeping motions of entire galaxies, a phenomenon that first hinted at the universe's deepest secret and continues to challenge our fundamental assumptions. For centuries, we've understood that gravity governs the dance of celestial bodies. Isaac Newton gave us the laws that describe how planets orbit stars, and Albert Einstein refined this picture, showing how mass and energy warp the fabric of spacetime itself. This framework works flawlessly within our solar system, allowing us to send probes to distant worlds with pinpoint accuracy. But when we zoom out to the scale of an entire galaxy, this elegant picture begins to fray at the edges in a most dramatic way. Imagine a vast spiral galaxy like our own Milky Way, a pinwheel of billions of stars spinning in the void. According to the established laws of gravity, the stars within this galaxy should behave much like the planets in our solar system. Those close to the dense center, where most of the visible mass is concentrated, should orbit very quickly. But as you move out toward the sparse outer edges of the galactic disk, the stars should be moving much more slowly, their speed dropping off in a predictable curve as the gravitational grip of the central mass weakens. This is simply how gravity and orbital mechanics are supposed to work. However, when astronomers like Vera Rubin and Kent Ford began meticulously measuring the rotational velocities of stars in distant galaxies in the 1970s, they found something that defied all expectations. The stars out on the very fringes of these galaxies were not slowing down. They were hurtling around at speeds just as high as the stars near the center. It was as if the entire galaxy was rotating like a rigid dinner plate, rather than a swirling vortex where the outer edges move slower. This was the discovery of the flat rotation curve, and it sent shockwaves through the field of astronomy. The immediate and most widely accepted solution was the existence of dark matter. The idea was that each galaxy must be embedded within a massive, invisible halo of some unknown material that provides the extra gravitational glue needed to keep these fast-moving outer stars from flying off into intergalactic space. This dark matter halo would be much larger than the visible galaxy itself, its gravity dominating the outer regions and explaining the constant orbital speeds. This revelation was monumental, completely reshaping our model of the universe. But as our observations have become more precise, a new layer of mystery has emerged. It turns out that the story isn't as simple as adding dark matter and calling it a day. Some galaxies, particularly small, diffuse dwarf galaxies, exhibit rotation curves that are too slow for the amount of dark matter our models say should be there. In other cases, like the well-studied spiral galaxy NGC 3198, the rotation curve remains stubbornly flat in a way that is incredibly difficult to replicate, even with sophisticated supercomputer simulations that try to model the behavior of dark matter particles. These persistent discrepancies have led a minority of physicists to pursue a radically different path. Instead of invoking vast amounts of invisible matter, they ask, what if our understanding of gravity itself is wrong on these enormous scales? This is the foundation of theories like MUND, which stands for Modified Newtonian Dynamics. MUND proposes a simple but profound tweak, that gravity behaves differently at extremely low accelerations, like those experienced in the outer reaches of galaxies. According to MUND, there is no need for dark matter. The unusual rotation curves are simply a consequence of a new law of gravity that kicks in where its pull becomes incredibly faint. While MUND does a surprisingly good job of predicting the rotation curves of many galaxies, it struggles to explain all the other evidence for dark matter, such as the gravitational lensing we see in galaxy clusters. This leaves us with a fascinating and unresolved tension. Do we stick with dark matter and try to figure out why its distribution is more complex and quirky than we first imagined, perhaps with different types of particles or unexpected interactions? Or do we take the more revolutionary step of rewriting the laws of gravity that have been a cornerstone of physics for centuries? The anomalous rotation of galaxies remains one of the most compelling clues that our cosmic model, in one way or another, is still incomplete. This puzzle of large-scale structure and motion finds a curious echo in our next phenomenon, which focuses not on the grand architecture of galaxies, but on the solitary wanderers drifting through the darkness between them. We've just explored how the very rotation of galaxies presents a fundamental challenge to our laws of physics, a puzzle that might be explained by invisible matter or a rewriting of gravity itself. Now let's shift our gaze from these colossal structures to the most solitary and lonely objects in the entire cosmos, worlds adrift in the eternal night. Picture a planet, perhaps even an Earth-sized world, but one utterly alone. There is no sunrise on this world, no warm star to orbit, no seasons, and no day from night. It is a permanent wanderer hurtling through the freezing, empty blackness of interstellar space, completely unbound by the gravitational pull of any star. These are rogue planets, and their existence in such vast numbers is one of the most surprising and counterintuitive discoveries in recent astronomy. For the longest time, our entire understanding of planets was inherently tied to stars. We defined them as bodies that orbit a star, and our own solar system seemed to be the perfect model, a neat, stable family of worlds circling a central sun. The prevailing theory was that rogue planets should be incredibly rare cosmic accidents. The primary method for their formation was thought to be a violent gravitational ejection. In the chaotic early days of a young solar system, as large protoplanets jostle for position, a close encounter can act like a gravitational slingshot, flinging a smaller world out of the system entirely, condemning it to an eternal journey through the void. Alternatively, some might form like stars do, directly from the collapse of small, isolated gas clouds that weren't quite large enough to ignite into a star, resulting in a failed star known as a brown dwarf. But both of these processes were considered rare. The ejection method requires a very specific and dramatic set of circumstances, and the direct collapse method was thought to produce only a handful of large, Jupiter-sized objects. Therefore, astronomers initially predicted that the galaxy would contain only a scattering of these lonely nomads. Then came the data from gravitational microlensing surveys. This ingenious technique doesn't look for light from these dark worlds. Instead, it watches for their gravity. When a rogue planet passes almost perfectly in front of a distant background star, its gravitational field acts like a tiny lens, bending and focusing the star's light for a brief period. This causes the background star to temporarily brighten in a very specific way. By monitoring millions of stars for these telltale flashes, projects like the Optical Gravitational Lensing Experiment, or OGLE, have provided a census of the invisible population drifting between the stars. The results were nothing short of staggering. The number of these microlensing events suggests that our Milky Way galaxy is not just home to a few rogue planets. It may be teeming with them, with estimates ranging from billions to, in some models, trillions of these free-floating worlds. They might vastly outnumber the stars themselves. This is a number so profoundly large that it completely upends our traditional models of planetary system formation. Take the rogue planet known as OGLE 2016 BLG 1928, discovered in 2020. This was a landmark detection because it was one of the smallest and most Earth-like rogue planets ever found, with a mass likely similar to Mars or Earth. Its microlensing event was incredibly brief, lasting only a few hours, which is a signature of a very low-mass object. The existence of such a small, terrestrial world floating freely in the darkness is a massive challenge to explain. If it was ejected from its home system, the process must have been exceptionally gentle and precise to avoid tearing the planet apart, yet powerful enough to give it escape velocity. The sheer number of these small, rocky rogues suggests that the early lives of planetary systems are far more violent and unstable than we ever imagined, with countless worlds being born only to be immediately exiled into the cold. This discovery doesn't just reshape planetary science, it also radically expands the potential for life in the universe. We once thought a planet needed to orbit within a star's Goldilocks zone, not too hot, not too cold, to have liquid water and potentially host life. A rogue planet with no star seems like the most lifeless place imaginable. But consider this, many of these worlds, especially larger ones, could retain heat from their formation and from the decay of radioactive elements in their cores. This internal heat could maintain vast, global subsurface oceans of liquid water, trapped beneath a thick, insulating shell of ice. In such an environment, life could potentially arise and persist around hydrothermal vents on the ocean floor, much like it does in the darkest depths of Earth's oceans, completely independent of any sunlight. The galaxy could be filled with these dark, aquatic worlds, each a potential island of life sailing silently through the interstellar sea. The idea that life might be thriving in such profound isolation forces us to rethink the very definition of a habitable world. The discovery of these countless nomadic planets reveals a universe far more dynamic, chaotic, and perhaps even more alive than we ever dreamed. Just as we grapple with the idea of countless orphaned worlds drifting unseen through the galaxy, our own solar system received a visitor that provided a stunning, first-hand example of the strange material that must be filling that interstellar void. In October 2017, astronomers in Hawaii made an unprecedented discovery using the Pan-STARRS telescope. They spotted a faint, fast-moving point of light that was unmistakably not from around here. Its extreme hyperbolic orbit, a path curving around our Sun at blistering speeds, was the definitive clue. This object was not bound by the Sun's gravity. It was merely passing through on its way from one star system to another. It was the first confirmed interstellar object ever detected, and it was given the name Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. From the moment of its discovery, Oumuamua was an enigma. The first puzzle was its shape. As it tumbled through space, its brightness varied dramatically, suggesting it had an extremely elongated, cigar-like form, perhaps 10 times longer than it was wide. This was unlike any asteroid or comet we had ever seen in our own solar system, where objects tend to be more lumpy and rounded, but the real head-scratcher came as it departed. After it whipped around the Sun and began its journey back out into deep space, something unexpected happened. Its trajectory was being very carefully tracked, and astronomers noticed it was accelerating ever so slightly, deviating from the precise path that gravity alone would dictate. This is a common behavior for comets, which contain ices that heat up near the Sun, turning into gas that jets out in a process called outgassing. This acts like a tiny, natural rocket engine, giving the comet a nudge. But Oumuamua showed no visible signs of this activity. There was no telltale coma, the fuzzy envelope of gas and dust that surrounds a comet's nucleus, and no tail streaming behind it. It was accelerating in complete silence and invisibility. This combination of bizarre traits, its interstellar origin, its strange shape, and its mysterious non-gravitational acceleration, sent scientists scrambling for explanations and inevitably captured the public's imagination. The most tantalizing, though least likely, hypothesis came from Harvard astronomer Avi Loeb, who suggested it could be a piece of alien technology, perhaps a light sail, a very thin, manufactured object pushed by the radiation pressure from starlight. While a captivating idea, the vast majority of the scientific community strongly favors natural explanations. The leading theory is that Oumuamua is indeed a comet, but a very exotic one. It might be composed of ices like solid hydrogen or solid nitrogen. As these ices were heated by the Sun, they would have sublimated directly from solid to gas, creating the thrust that accelerated it without producing the dusty debris that would normally create a visible coma. Alternatively, it could be a fractal-like aggregate of dust, a porous, snowflake-like structure that is mostly empty space, which would explain its unusual acceleration from the gentle push of escaping gas and its strange light curve. The most profound implication of Oumuamua's visit isn't necessarily what it was, but the simple fact that it was. For it to be the first object of its kind we've ever seen, the statistics suggest that our interstellar neighborhood must be absolutely filled with such debris. Estimates suggest there could be thousands of similar objects within the orbit of Neptune alone at any given time, and quadrillions of them drifting through the galaxy between stars. We simply hadn't noticed them before because they are so small, dark, and fast. Oumuamua was a tiny glimpse into the vast and diverse zoo of objects that must exist out there, the leftover building blocks from other star systems, the fragments of planetary collisions, the icy planetesimals ejected from their homes. It tells us that the space between stars is not a perfect void. It is a cosmic highway busy with traffic of all shapes and sizes, most of it utterly foreign to anything we know in our own solar system. This realization that interstellar space is crowded with ordinary yet mysterious matter provides a perfect segue into a related but even more fundamental cosmic accounting error. The mystery of Oumuamua and the countless rogue planets hint at a cosmos filled with far more material than we can easily see, but this leads us to an even more fundamental cosmic accounting error, one that strikes at the very inventory of the universe's ordinary building blocks. We now turn to a puzzle not about dark matter or exotic visitors, but about the familiar stuff we're made of, the protons and neutrons known collectively as baryons. After the Big Bang, the universe created a specific amount of this ordinary matter, the stuff that makes up every star, planet, and person. By studying the faint afterglow of the Big Bang, the cosmic microwave background, scientists have been able to conduct a precise cosmic census, calculating exactly how much of this baryonic matter should exist today. The number is clear and definitive, yet when astronomers add up all the baryons they can actually observe, all the stars twinkling in galaxies, all the glowing gas clouds within them, and all the dust floating between them, they come up dramatically short. The count reveals that a staggering 30 to 40% of the universe's expected ordinary matter is simply missing. It's as if you meticulously counted every piece of furniture in your house from a blueprint, only to walk through the rooms and find that nearly half of the chairs, tables, and beds have vanished into thin air. This is the missing baryon problem, and it represents a huge gap in our understanding of the cosmos's basic composition. So, where could this enormous amount of matter be hiding? The leading suspect is a ghostly, diffuse network of gas known as the warm-hot intergalactic medium, or WIM. Theorized to exist in the vast spaces between galaxies, the WIM is believed to be composed of incredibly hot but incredibly thin gas, heated to temperatures of hundreds of thousands or even millions of degrees by the gravitational shocks of forming large-scale cosmic structures. This gas is so tenuous and so hot that it doesn't emit much visible light. Instead, it primarily glows in low-energy X-rays, making it fiendishly difficult to detect with conventional telescopes. It's the equivalent of trying to spot the faint heat haze rising from a single candle from a mile away on a hot day. The hunt for this elusive matter has been a painstaking endeavor. Astronomers have employed a clever trick. They don't look for the WIM directly. Instead, they use the brightest objects in the universe as backlights. When the light from a distant quasar, a brilliantly luminous galactic core, travels billions of light years to reach us, it passes through these invisible filaments of hot gas. Atoms within the WIM, like oxygen and hydrogen, absorb very specific wavelengths of this light. By analyzing the quasar's spectrum with powerful instruments like the Chandra X-ray Observatory, scientists can search for the faint, telltale dips in the light that signal the presence of these absorbing atoms. And they have found them. There have been tantalizing detections, moments where the signature of the WIM has been glimpsed, confirming that this warm hot gas does indeed exist in the cosmic web. But here's the frustrating part. Even when we add up all the WIM we've managed to detect so far, the numbers still don't balance. The total mass found in these filaments is significant, but it still doesn't account for the full 30 to 40% of missing baryons. This leaves us with a few unsettling possibilities. perhaps the whim is even more widespread and hotter than our current models predict, making it even more difficult to see. Maybe the missing matter is hiding in an even more elusive form, perhaps in vast, faint halos around galaxies that our current telescopes cannot resolve. Or there's the more radical possibility that our understanding of the physics governing the early universe, derived from the cosmic microwave background, is somehow incomplete. This isn't just an academic exercise. Solving this mystery is crucial for understanding the entire life cycle of the cosmos. This missing matter is the very raw material from which galaxies form and evolve. If we can't account for it, our models of how structures grew from the smooth early universe into the web of galaxies we see today are fundamentally flawed. The hunt for these missing baryons is a cosmic detective story, a meticulous search for the hidden material that makes up a significant portion of everything we are. This puzzle of invisible, ordinary matter sets the stage perfectly for our next phenomenon, where we will explore a different kind of emission, one that involves not the absorption of light, but its mysterious and anomalous creation. After searching the vast cosmos for missing atoms, we now turn our attention to a different kind of mystery, one that doesn't involve something being absent, but rather something unexpected appearing. This enigma comes to us not in the form of visible light or high-energy particles, but from a much more familiar part of the spectrum, the microwave. In our daily lives, microwaves are associated with heating food or transmitting data, but out in the depths of space, they are telling a strange and unexplained story. Across the galaxy, astronomers have mapped out a faint, pervasive glow of microwave radiation that shouldn't be there according to our standard models. This is known as anomalous microwave emission, or AIM, and it represents a classic case of the universe presenting us with a signal and daring us to figure out what it means. For a long time, when astronomers detected microwaves coming from regions of space rich with gas and dust, like molecular clouds where new stars are born, they had a ready explanation. They believed this emission was primarily caused by two well-understood processes. The first is synchrotron radiation, which is generated by high-energy electrons spiraling around magnetic field lines. The second is thermal radiation, which is simply the heat emitted by warm dust. But as our instruments became more sensitive, particularly with space-based observatories like the Planck satellite, which was designed to map the cosmic microwave background in exquisite detail, a third, unexpected signal kept appearing. This signal had a unique spectral signature. Its brightness changed with wavelength in a way that didn't match either synchrotron or thermal radiation. It was something entirely new, and it was dubbed anomalous because it had no clear, agreed-upon origin. The most promising theory, and the one that initially seemed to solve the puzzle, involved tiny, spinning dust grains. Imagine countless nanoscale diamonds or other carbon-based molecules, smaller than a particle of smoke, spinning at incredible rates billions of times per second. According to this idea, the electric dipole moment of these tiny spinning grains would cause them to emit radiation right in the microwave part of the spectrum. This mechanism, known as spinning dust emission, became the leading candidate. It elegantly explained why AME was often found co-located with dense clouds of interstellar dust. The raw material was right there. For a while, it seemed the case was closed. However, the universe rarely allows for such neat and tidy solutions. As researchers looked closer, inconsistencies began to emerge. The intensity and specific characteristics of the anomalous emission didn't always perfectly match the predictions of the spinning dust model. In some regions, the microwave signal was far stronger than it should have been for the amount of dust present. In other areas, the spectrum of the light, the precise way its intensity varied across different microwave frequencies had peculiar features and bumps that the simple model of spinning grains couldn't replicate. A prime example of this stubborn complexity is found in the Perseus molecular cloud, a massive star-forming region about 1,000 light-years away. Here, AMI is clearly detected and correlates with the presence of dust, but its properties are just different enough to raise serious questions. The signal is either too strong, too weak, or has the wrong shape compared to what theory dictates. This persistent mismatch has forced scientists to consider other, more exotic explanations. Perhaps the emission isn't coming from spinning dust at all, but from something entirely different. One compelling alternative is magnetic dipole radiation. This proposed mechanism involves not the rotation of dust grains, but the oscillation of atoms within tiny magnetic mineral grains like interstellar iron particles. As these atoms jiggle under the influence of heat, their magnetic fields fluctuate, potentially producing microwave radiation. Other theorists have pondered whether unknown chemical processes on the surfaces of dust grains could be responsible, or even the presence of specific, large molecules like polycyclic aromatic hydrocarbons that might be releasing energy in this unique way. The solution to this mystery is more than just an academic exercise. It has real, practical implications for our understanding of the cosmos. The most famous microwave signal in the universe is the cosmic microwave background radiation, the ancient afterglow of the Big Bang. Cosmologists study the tiny fluctuations in this background radiation to understand the origins and composition of our universe. But to see it clearly, they must first subtract all the other sources of microwave emission that lie in the foreground between us and the edge of the observable universe. Anomalous microwave emission is one of the most significant and frustrating of these foreground signals. If we don't fully understand what AMI is and how it behaves, we cannot accurately remove it, which means our picture of the early universe becomes blurred and less precise. Unraveling the nature of AMI is therefore essential for cleaning our cosmic lens and seeing further back in time than ever before. This puzzle of mysterious energy emission, tied to the interplay of dust and forces we can scarcely see, provides a perfect conceptual bridge to our next great interstellar mystery, which involves forces that shape the cosmos on a truly grand scale. Just as we unravel the mystery of anomalous microwave emissions, we find ourselves drawn to the invisible forces that may very well be shaping them, the cosmic magnetic fields that weave through the void like ghostly threads. We often think of space as an empty, passive stage, but it is in fact crisscrossed by these powerful, dynamic fields generated by the motion of charged particles in plasma. They are the universe's great sculptors, guiding the collapse of gas clouds into new stars, channeling the paths of high-energy cosmic rays, and even influencing the formation of the largest structures in the cosmos. Their presence is felt everywhere, from the hearts of galaxies to the vast, seemingly empty expanses between them. And it is in these deepest voids that these magnetic fields present us with one of their most stubborn puzzles: their inexplicable persistence and surprising uniformity. According to our fundamental understanding of electromagnetism, a magnetic field should not be able to sustain itself forever without a source. The charged particles and electric currents that generate these fields should gradually dissipate, their energy slowly bleeding away into the void, causing the fields to weaken and fade over millions of years. This is especially true in the immense cosmic voids, those regions of space that are largely devoid of galaxies and the dense plasma that could act as a natural power source. These are the emptiest places in the universe, and yet, when astronomers use sophisticated techniques to measure magnetic fields there, often by observing how they polarize the light from distant radio sources, or how they influence the propagation of cosmic rays, they find that the fields are not only present, but they are also remarkably coherent and structured over staggering distances. They endure with a strength and consistency that defies their predicted decay. This resilience points to a fundamental gap in our knowledge. How are these fields being maintained? The leading theory involves a process called a dynamo, where the motion of conductive plasma can amplify a weak seed magnetic field, much like a turbine generates power here on Earth. On a galactic scale, the rotation of a galaxy and the turbulent motions within its disk could theoretically serve as a massive dynamo, strengthening and sustaining its magnetic field. But this theory hits a wall when we try to apply it to the voids. There simply isn't enough detectable plasma or large-scale motion in these empty regions to power such a dynamo effect. The energy source for this cosmic maintenance is missing. Observations from powerful instruments like the Planck satellite have only deepened the mystery. Planck's all-sky maps of polarized light have revealed that magnetic fields are not just local features. They are coherent across entire galaxy clusters, spanning millions of light-years. The fields show a surprising degree of order, with lines often aligned over these incomprehensibly vast scales. This large-scale coherence is a massive clue. It suggests that these fields might be primordial, a fossil relic from the universe's very birth. The idea is that incredibly weak magnetic fields could have been generated in the violent, seething plasma of the Big Bang itself. As the universe expanded and cooled, these fields would have been stretched and frozen into the fabric of space-time, providing the initial seed that later dynamo processes could then amplify within galaxies. This primordial origin story is compelling, but it too is fraught with challenges, as the mechanisms for generating such fields in the early universe remain highly speculative and poorly understood. The implications of solving this mystery are profound. Interstellar and intergalactic magnetic fields play a critical role in virtually every astrophysical process. They provide the scaffolding that supports giant molecular clouds as they collapse to form stars and planets. They act as colossal particle accelerators, whipping charged particles like protons and electrons to nearly the speed of light, creating the cosmic rays we detect here on Earth. They regulate the flow of heat and matter within galaxies and even influence the growth of cosmic structures. If we don't understand how these fields originate and sustain themselves, our models of cosmic evolution are built on an incomplete foundation. The enduring strength of magnetic fields in the void is a silent testament to a deep and ongoing physical process that we have yet to decipher, a hidden engine humming in the darkness that keeps the cosmic machinery running. This invisible, pervasive force sets the stage for one of the most violent and energetic events in the entire cosmos. From the invisible, pervasive force of magnetic fields weaving through the cosmos, we now turn to one of the most violently energetic events. Those fields can help shape a celestial explosion so powerful it can outshine an entire galaxy of stars, but one that overstays its welcome in a way that defies all expectations. Gamma-ray bursts are already the universe's most formidable blasts, typically marking the catastrophic death of a massive star in a supernova or the violent merger of two ultra-dense neutron stars. These events are normally incredibly brief, unleashing their unimaginable fury in a flash of high-energy gamma rays that lasts from mere milliseconds to a couple of minutes at most. Their incredible brevity is a key clue to their origin. They are the final, desperate scream of a stellar system being torn apart in an instant. But then there are the outliers, the cosmic rebels that break all the rules. Astronomers have discovered a rare and perplexing class of these events known as ultra-long gamma-ray bursts. As the name implies, these are GRBs that simply refuse to die quickly. Instead of a fleeting flash, they persist. They can pour out gamma radiation for several minutes, and in the most extreme cases, for hours on end. One of the most famous examples is GRB 1,112,090A, an event detected in December 2011 that unleashed a continuous torrent of gamma rays for over 7 hours. This is not a mere difference in degree, it is a fundamental difference in kind. It's the difference between a firecracker and a raging wildfire. Such a prolonged duration immediately tells us that the engine powering this explosion cannot be the same as that of a typical, short-lived GRB. So, what celestial powerhouse could possibly sustain such an incredible output for so long? The leading theory points to a very specific and rare type of star, a blue supergiant. These are massive, evolved stars that are hundreds of times larger than our Sun. Imagine a star so vast that if it were placed at the center of our solar system, its outer surface might extend beyond the orbit of Jupiter. Theorists propose that when such a behemoth reaches the end of its life and collapses, it could form a different kind of system than a typical supernova. Instead of a quick, violent collapse and explosion, the star's immense size could create a situation where a newly formed black hole or neutron star at its core continues to feed on the star's enormous outer envelope for an extended period. This would be a stellar death by prolonged consumption, not a sudden detonation. The infalling material forms a vast accretion disk around the central object, and the immense gravitational energy released, along with powerful jets punching through the star's poles, would act as a long-lasting engine for the gamma-ray burst. Another compelling candidate is the birth of a magnetar, a newly formed neutron star with an almost incomprehensibly powerful magnetic field, trillions of times stronger than Earth's. As this incredibly dense, rapidly spinning object forms, its immense magnetic fields can get tangled and release enormous amounts of energy in a process that could, in theory, power a longer-lasting burst. However, both of these models run into a significant problem: the energy budget. The sheer amount of gamma radiation emitted during these ultra-long events is often staggeringly high, pushing the limits of what even these powerful engines are thought to be capable of producing. It forces us to ask if our understanding of the physics inside a collapsing star is complete, or if there is some other, even more efficient process at work that we haven't yet imagined. Our window into these distant cataclysms comes from space-based observatories like NASA's Neil Gehrels Swift Observatory and the Fermi Gamma Ray Space Telescope. These satellites are our sentinels in the void, constantly scanning the skies for the telltale flash of a GRB. When they detect one, they instantly slew to point their other instruments at it, measuring the afterglow, the fading emission at X-ray, ultraviolet, and optical wavelengths that lingers after the initial gamma-ray flash has faded. This afterglow is crucial. It acts like a cosmic forensic report, allowing astronomers to determine the burst's distance, its host galaxy, and the properties of the surrounding interstellar environment it illuminated. Many ultra-long GRBs are found to be associated with supernova, confirming their link to stellar deaths, but often in environments that are poorer in heavy elements than our own galaxy, which might influence the type of massive stars that form there. The enduring mystery of ultra-long GRBs is a classic example of a cosmic anomaly that forces us to refine our theories. They represent a critical stress test for our models of stellar astrophysics and high-energy processes. Solving their puzzle could reveal new pathways of stellar evolution, teach us about the diversity of stellar deaths in different cosmic environments, and even provide new insights into the birth mechanisms of black holes and magnetars. They are a brilliant, prolonged, and deeply puzzling signature in the sky, a testament to the fact that even in death, stars can surprise us in the most spectacular ways. This exploration of immense energy and prolonged violence in the cosmic tapestry finds a striking contrast in our next destination, where we will explore the profound and mysterious nothingness that exists between the threads. After exploring the prolonged fury of ultra-long gamma-ray bursts, we now journey into the polar opposite of cosmic extremes, the immense, silent, and almost unfathomably empty regions known as cosmic voids. If the universe's large-scale structure is a vast cosmic web, with galaxies and galaxy clusters tracing its bright filaments and dense nodes, then these voids are the dark, gaping holes in that web. They are the universe's true deserts, realms of profound nothingness that stretch for hundreds of millions of light years. The very existence of these voids and their startling properties presents a direct challenge to our most fundamental theories of how the universe evolved from a smooth, hot soup of particles into the structured tapestry we see today. The largest of these voids defy easy comprehension. Take, for instance, the Boötes void, also poetically known as the Great Nothing. Discovered in the 1980s, this region of space is a staggering 250 million light-years across. To put that impossible scale into perspective, if you could travel at the speed of light, it would take you 250 million years to go from one side to the other. Within this incomprehensible volume, astronomers have found only a handful of galaxies, where according to standard models of structure formation, there should be thousands. It is a volume of space so empty that if our Milky Way were placed at its center, we would have had no knowledge of other galaxies until the 1960s. This is not just an absence of bright objects, it is a region where the density of matter, both normal and dark, plummets to a small fraction of the cosmic average. According to our prevailing cosmological model, which includes the inflationary Big Bang theory and the influence of dark matter, the universe should not have voids this large or this empty. The early universe was remarkably smooth, as evidenced by the cosmic microwave background. The slight quantum fluctuations imprinted during inflation were then amplified by gravity over billions of years. Dark matter acted as the gravitational scaffolding, pulling normal matter into the filaments and nodes and leaving behind the voids. But the process should have been more gradual and uniform. The existence of supervoids like the one in Boötes suggests that either the initial seeds for these structures were far larger than inflation should allow, or that another force has been actively at work, sculpting and emptying these regions far more effectively than gravity alone. This is where the mystery of dark energy intensifies. Dark energy is the name we give to the mysterious force causing the accelerated expansion of the universe. We expect this expansion to be happening everywhere, but its effects might be most pronounced in the voids. In the dense environments of galaxy clusters, the powerful gravitational pull of all that matter fights back against dark energy's repulsive force. But in the voids where gravity's grip is weakest, there is nothing to resist it. Think of it like this: the universe's expansion is like a rising tide, but in the voids, it's as if the tide is rising faster, causing these empty regions to become even larger and more diluted over time. Some cosmologists even speculate that the properties of dark energy itself could be different inside these voids, or that our theory of gravity needs modification in these extremely low-density environments to account for their anomalous emptiness. But the voids are not completely empty. Deep imaging surveys have revealed that they are sparsely populated with isolated, faint dwarf galaxies. Furthermore, despite their incredible lack of visible matter, they are not entirely free of gravity's influence. The subtle gravitational tug of a void can actually leave a faint imprint on the cosmic microwave background, an effect known as the integrated Sachs-Wolf effect. This tells us that while these regions are vast deserts, they still contain traces of dark matter, perhaps in the form of faint, unseen filaments that weave through the nothingness. The precise arrangement and sheer scale of these voids force us to constantly refine our simulations of cosmic evolution. Each new, larger void we discover pushes the limits of our standard model of cosmology, suggesting that our universe might be even more structured and complex on the largest scales than we ever thought possible. This profound emptiness, a dominant feature of our cosmos, stands in stark contrast to the impossibly energetic particles we will consider next. If the vast, echoing emptiness of cosmic voids represents one extreme of our universe, then the particles we are about to discuss represent the very opposite, a concentrated fury of energy so immense it seems to break the universe's own speed limits. We are returning to the realm of cosmic rays, but not just any cosmic rays. These are the ultimate outliers, the universe's most energetic particles, and their very existence throws a wrench into a fundamental prediction made over half a century ago. In 1966, three physicists, Kenneth Greisen and Georgy Zatsepin and Vadim Kuzmin, made a startling calculation based on the well-established laws of special relativity and particle physics. They realized that the universe itself should impose a strict speed limit, an energy ceiling, on protons and atomic nuclei traveling across intergalactic space. This theoretical barrier became known as the GZK Cutoff. The reasoning behind this cutoff is both elegant and inescapable. Our universe is not a perfect vacuum. It is gently warmed by the faint, cold glow of the cosmic microwave background radiation, the ancient afterglow of the Big Bang. This background radiation is composed of countless low-energy photons that fill every cubic centimeter of space. For you and me, these photons are utterly harmless, but for a proton traveling at almost the speed of light, they become a formidable barrier. According to the physics worked out by Einstein, when an ultra-high-energy proton slams into one of these background photons, the collision should be so violent that it triggers a nuclear reaction. The proton would produce a short-lived particle called a pion, in the process losing a significant fraction of its colossal energy. Over a long journey of 150 million light-years or so, this process would happen again and again, relentlessly sapping the proton's energy until it falls below the GZK limit. It's a cosmic drag race where the universe always wins, ensuring that no proton from a distant galaxy should ever reach Earth with an energy above this threshold. For decades, this was a beautiful and untested prediction. Then, our detectors got better. Facilities like the telescope array in the Utah desert and the Pierre Auger Observatory in Argentina are not traditional telescopes. They are vast networks of sensors that cover thousands of square kilometers, designed to catch the fleeting, secondary showers of particles created when a single cosmic ray slams into the top of our atmosphere. The data they have collected is unequivocal and mind-bending. The GZK cutoff is being violated. Particles are arriving at Earth with energies that, according to the established laws of physics, they simply should not have after traveling across the universe. The most famous of these is the aforementioned "Oh my God" particle, detected in 1991. The energy carried by that single subatomic particle was breathtaking, equivalent to a well-thrown baseball, all packed into a speck 1 trillion times smaller than a grain of sand. It was moving so inconceivably close to the speed of light that in a race with a beam of light from a distant quasar, it would lose by less than the width of a human hair. The immediate and most logical explanation is that these particles must come from somewhere relatively close by, within our local cosmic neighborhood of about 150 million light-years, a distance often called the GZK horizon. Within that range, the particle wouldn't have had time to be slowed down by the photon sea. So, astronomers have scrambled to find the cosmic accelerators responsible. The suspects are the usual, incredibly powerful astrophysical engines, active galactic nuclei, where supermassive black holes devour matter and blast out jets of particles, gamma-ray bursts, the most violent explosions since the Big Bang, or perhaps the colossal shockwaves from merging galaxy clusters. The problem is, when we trace the paths of these ultra-high-energy cosmic rays back to their points of origin, we often find nothing. The sky in that direction is empty, or the nearest candidate object is far beyond the GZK horizon. It's as if a cannonball has landed at our feet, but there is no cannon in sight. This leaves scientists with a far more exciting and far more unsettling set of possibilities. If these particles aren't coming from nearby, then they are defying the GZK cutoff itself. This forces us to consider that our understanding of physics itself might be incomplete at these extreme energies. One radical theory is a violation of Lorentz invariance, a cornerstone of Einstein's special relativity. This principle states that the laws of physics are the same for all observers, regardless of their constant velocity. If Lorentz invariance is violated at these incredible energies, it could mean that the pion creation reaction doesn't happen as expected, allowing the protons to travel unimpeded across the universe. Other theories propose new types of particle interactions, or that these cosmic rays are not protons at all, but heavier nuclei like iron, which might behave differently. There's even the speculative idea that they could be the signature of decaying super-heavy dark matter particles, annihilating in the halo of our own galaxy, and creating these monstrously energetic particles right in our backyard. Each of these explanations would require a profound rewriting of physics textbooks. The detection of these particles is more than just a record-breaking curiosity. It is a direct experimental challenge to our most fundamental theories. They are messengers from the most violent and unknown corners of the cosmos, carrying information that our current models cannot decode. Their impossible journey forces us to confront the possibility that the rules of the game change at energies we can scarcely imagine, hinting at a deeper layer of reality governed by a physics we have yet to discover. This confrontation with the fundamental laws that govern matter and energy naturally leads us to question another pillar of modern physics, the way the universe handles the very fabric of time itself. We have just witnessed how particles can seemingly defy the universe's own speed limits, challenging the very foundations of relativistic physics. Now, we venture into a concept that is even more fundamental to our experience of reality: the steady, reliable flow of time itself. According to Albert Einstein's revolutionary theory of general relativity, time is not a universal constant ticking away at the same rate for everyone. Instead, it is a flexible dimension warped and stretched by the presence of mass and energy. This effect, known as gravitational time dilation, means that a clock ticks more slowly the closer it is to a powerful gravitational source. We have confirmed this with stunning precision right here in our own cosmic backyard. The atomic clocks on GPS satellites in orbit, experiencing slightly less gravity than we do on Earth's surface, actually run faster by a tiny but measurable amount. If engineers didn't constantly correct for this relativistic effect, your phone's navigation would be off by several miles within a single day. But what happens when we push this well-tested theory to its absolute limits, into the most extreme environments the universe has to offer? This is where tantalizing anomalies may be hiding, around the most massive and dense objects in existence, like the supermassive black holes at the centers of galaxies or in the frantic dance of binary pulsar systems. Astronomers are looking for any subtle discrepancy between what Einstein's equations predict and what they actually observe. In these regions, gravity is so intense that it doesn't just bend the path of light. It twists the very fabric of space-time itself into knots. One of the most promising laboratories for this investigation is the star cluster orbiting our own galaxy's central black hole, Sagittarius A. By meticulously tracking the orbits of these stars for decades, scientists can test whether the time dilation experienced by a star on a close, high-speed approach to the black hole perfectly matches the predictions of general relativity. Any deviation, however minute, would be a monumental discovery. The challenge is that these effects are incredibly small and the distances are vast, making precise measurement extraordinarily difficult. While our Earth-based and satellite experiments have confirmed relativity to an incredible degree, we have not yet been able to conduct similarly precise tests of time dilation in the deep gravity wells of distant neutron stars or black holes. This experimental gap leaves a window open for extraordinary possibilities. Some theories of quantum gravity, which seek to unify general relativity with quantum mechanics, predict that under these extreme conditions, the smooth, continuous geometry of spacetime described by Einstein might break down into a kind of frothy, granular foam at the tiniest possible scales. This quantum foam could potentially introduce tiny, random fluctuations in the flow of time itself, creating anomalies that would appear as a slight stutter or hiccup in the otherwise smooth slowing of time. Other revolutionary ideas suggest that the presence of extra dimensions of space, as predicted by string theory, could subtly alter how gravity behaves in these extreme regimes, leading to observable differences in how time dilates. The implications of discovering such an anomaly are almost beyond comprehension. It would not merely be a small adjustment to a scientific formula. It would represent a crack in our fundamental understanding of reality. It would be direct evidence that our current theory of gravity, as successful as it has been, is an approximation of a deeper, more complete theory that operates at the quantum level. Proving that time itself can behave in unexpected ways would force a radical rewriting of physics and could provide the first experimental clues to a theory of everything. This exploration of time's potential mutability leads us directly to an even more profound question. If time itself might not be constant, what about the other fundamental rules of the universe? If the very flow of time can be warped by gravity, bending to the will of massive objects, then it forces us to ask an even more unsettling question about the cosmos. Are the rules themselves written in stone, or could they be changing? We now arrive at a concept so foundational that questioning it feels like pulling a thread that could unravel the entire tapestry of physics. The idea that the fundamental constants of the universe might not be so constant after all. These constants are the fixed numerical values that appear in the laws of physics, the immutable settings that dictate how reality operates. They are the universal dials that control the strength of forces, the masses of particles, and the very fabric of spacetime. The fine structure constant, often denoted by the Greek letter alpha, is one of the most crucial. It governs the strength of the electromagnetic force, which is responsible for holding atoms together, making chemistry possible, and essentially creating the world we see and touch. For decades, the unwavering assumption has been that this number, approximately 1/137, is the same everywhere in the universe and has been the same for all time. It is a cornerstone of our entire physical model. The first serious challenge to this deeply held belief emerged from a seemingly impossible place, the light of impossibly distant quasars. These brilliant beacons, the cores of active galaxies billions of light years away, act as cosmic lighthouses. As their light travels across the vastness of space to reach us, it passes through clouds of interstellar and intergalactic gas. Atoms within these clouds absorb specific wavelengths of this light, leaving behind a unique fingerprint in the quasar's spectrum, a series of dark lines that act as a barcode for the elements present. When astronomers like John Webb and his team analyzed these absorption lines with powerful telescopes like the Very Large Telescope in Chile, they noticed something peculiar. The patterns of these lines, specifically the spacing between them, which depends on the value of the fine structure constant, seemed to be slightly shifted. The implication was staggering. The data suggested that the strength of electromagnetism was different in those distant regions of space and time. It was as if the universe's dials had been tweaked. But this is where the scientific process shines, and the mystery deepens into controversy. These measurements are at the very bleeding edge of precision, requiring astronomers to disentangle the signal from an ocean of noise and potential systematic errors. Other teams using different instruments and methodologies, such as observations from the Keck Observatory in Hawaii, have looked at different patches of the sky and failed to confirm the same result. They found no evidence of a changing constant. This has created a tense and fascinating scientific debate. Is the detected variation a genuine discovery, a whisper from the cosmos that our laws are local and not universal? Or is it a subtle artifact of the immense difficulty of the measurement, a ghost in the machine of our most advanced telescopes? The controversy itself is a testament to how profound the implications would be. If this variation were confirmed, it would be nothing short of a scientific revolution. It would mean that the laws of physics are not the same everywhere. The universe could have domains where chemistry works slightly differently, where the stability of atoms varies, and where the very possibility of life as we know it could be altered. This would immediately point toward theories beyond our standard model, perhaps involving extra dimensions predicted by string theory. In such models, what we perceive as fundamental constants in our three-dimensional space might actually be the visible shadows of more complex fields vibrating in higher dimensions, fields that could slowly evolve over cosmic time. Alternatively, it could provide a compelling piece of evidence for the multiverse hypothesis. In an infinite multiverse, every possible value for these constants could be realized in a different universe. We simply live in one where the numbers are perfectly tuned for our existence. The mere possibility that these constants might vary forces us to confront the deepest nature of reality, questioning whether our physical laws are truly fundamental or merely local bylaws in a much grander cosmic structure. This profound question about the stability of the universe's rules leads us directly to the search for the oldest possible relics, echoes from the very moment those rules were supposedly set. The quest to understand the fundamental constants of the universe inevitably leads us back to the very beginning, to a fraction of a second after the Big Bang, when the entire cosmos is thought to have undergone a growth spurt of unimaginable speed and scale. This theoretical period, known as cosmic inflation, is a cornerstone of modern cosmology. It elegantly explains why the universe appears so remarkably uniform in all directions, and how the tiny quantum seeds for all future structure, galaxies, stars, and planets were first planted. But like any grand historical event, such a violent and pivotal chapter should have left behind forensic evidence, unmistakable relics for us to discover. The frustrating and profound mystery is that these predicted echoes from the dawn of time have remained stubbornly elusive, casting a fascinating shadow of doubt over our entire origin story. The most sought after of these relics are primordial gravitational waves. Inflation proposes that the universe expanded faster than the speed of light itself, driven by a mysterious inflationary energy field. Such a violent, rapid stretching of spacetime would have created massive ripples in the very fabric of the cosmos' gravitational waves, originating from the universe's first moments. Unlike the waves detected from black hole mergers by LIGO, these primordial waves would have a much longer wavelength and would have imprinted a unique pattern on the oldest light we can see, the cosmic microwave background. This pattern, known as B-mode polarization, would appear as a faint, swirling curl in the polarization of the CMB, a direct signature of inflation's gravitational shock waves. Finding this pattern would be the ultimate smoking gun, providing a direct glimpse into the physics of the universe when it was less than a trillionth of a second old. The hunt for this signal reached a fever pitch in 2014 with the BICEP-2 experiment, a powerful telescope located at the South Pole where the cold, dry air is perfect for such precise observations. The team announced a historic discovery. They had detected the telltale B-mode polarization. For a brief, exhilarating moment, it seemed we had finally found the evidence for inflation. But the triumph was short-lived. Further analysis, most critically using data from the Planck satellite, revealed a devastating confounding factor. The signal they had seen was not from the dawn of time. It was caused by something much more mundane and local: interstellar dust within our own galaxy. This dust, when illuminated by starlight and viewed at certain angles, can polarize light in a way that perfectly mimics the inflationary signal BICEP-2 was seeking. It was a sobering lesson in cosmic forensics, where contamination from a nearby source can completely obscure the ancient evidence. Another predicted relic from this era is even more exotic: the magnetic monopole. In our everyday experience, magnets always have two poles, a north and a south. You can break a magnet in half, and you'll just get two smaller magnets, each with its own north and south pole. However, most grand unified theories, which attempt to merge the electromagnetic, weak, and strong nuclear forces, predict that in the extreme energy conditions of the very early universe, particles carrying a single magnetic charge, either a north or a south, should have been created in abundance. These magnetic monopoles would be incredibly massive, stable, and should still be around today, a fossil population from the universe's highest energy phase. Despite extensive and creative searches, from analyzing ancient mica crystals deep underground to scanning the moon's surface, not a single confirmed magnetic monopole has ever been found. Their absence is a major puzzle, often called the monopole problem, and was one of the key motivations for proposing inflation in the first place, as the rapid expansion would have diluted their density to undetectable levels. The continued absence of these definitive relics forces cosmologists to confront some uncomfortable possibilities. Perhaps the simplest explanation is that our specific models of inflation are wrong. There are hundreds of proposed inflationary models, each with slightly different predictions for the strength of the gravitational waves produced. It's possible that inflation did happen, but in a much gentler, lower energy way that produced gravitational waves too faint for our current instruments to detect. Alternatively, the entire paradigm might need a significant revision. Maybe the universe began in a way that is entirely different from the inflationary picture we've grown so fond of. Some theorists are exploring cyclical models of the universe or scenarios emerging from a quantum bounce, ideas that would not necessarily produce the same relics. This gap in our knowledge has profound ripple effects, especially for theories that attempt to go beyond the standard model of particle physics, such as string theory. String theory, which posits that the fundamental building blocks of the universe are tiny, vibrating strings, often predicts a vast landscape of possible universes, each with different physical laws and constants. Many versions of string theory are intimately tied to the inflationary framework, and the failure to detect its predicted relics places constraints on which versions of these theories could be viable. Without this crucial empirical evidence from the universe's birth, these elegant mathematical constructs remain suspended in a realm of beautiful speculation, untethered from observable reality. The silence from the cosmos's first moment is a powerful message, reminding us that our most cherished theories about creation are still waiting for their final verdict from nature itself. This challenge of detecting the seemingly undetectable from the ancient past finds a direct parallel in our next great mystery, which involves searching for an invisible substance hiding in the present. For decades, the hunt for dark matter has followed a straightforward, if immensely challenging, path: find the particle. The prevailing theory, known as cold dark matter, envisions a universe teeming with massive, slow-moving particles that interact with normal matter only through gravity and perhaps the weak nuclear force. This model has been spectacularly successful on a grand scale, perfectly explaining the formation of galaxies and the large-scale structure of the cosmos. But it makes a critical prediction: these particles, often called WIMP, should occasionally bump into the nuclei of atoms in ultra-sensitive detectors buried deep underground. After decades of searching with ever more sophisticated experiments, these direct detection efforts have largely come up empty. The silence is deafening, forcing physicists to confront a radical and humbling possibility. What if dark matter isn't just hiding? What if it's fundamentally stealthy, designed by nature to be nearly impossible to see? This growing frustration has given rise to a fascinating new class of theories: stealth dark matter models. These are not your grandfather's WIMP. Instead of weakly interacting massive particles, imagine dark matter that is feebly interacting, or even non-interacting, with itself and with us. The goal is to explain all the gravitational evidence for dark matter's existence while simultaneously explaining why we haven't found it. One compelling idea is asymmetric dark matter. In the visible universe, there's a profound asymmetry. Matter vastly outweighs antimatter. Why couldn't a similar asymmetry exist in the dark sector? In this model, dark matter particles are their own antiparticles, but a process in the early universe created a vast surplus of one type, leaving no partners to annihilate with and produce the telltale signals we've been searching for. It would be a dark universe that is quiet and stable, its particles simply flowing through each other and through us without a trace. Another intriguing concept places dark matter within a so-called hidden sector. This is a hypothetical realm of particles and forces that parallel our own, but which communicate with normal matter only through the faintest of connections, perhaps only gravity. In this shadow universe, dark matter could be rich and complex, potentially even having its own dark forces, dark photons and dark chemistry, all completely invisible to our instruments. A dark matter particle in this sector might interact strongly with its own dark radiation, but because that radiation doesn't couple to our electromagnetic field, we would be completely blind to its internal dynamics. It would only reveal its presence by its collective gravitational weight. This shift in thinking radically changes the game for experimentalists. If dark matter has no interactions beyond gravity, then the decades-long strategy of building underground traps to catch a rare collision is doomed to fail. How do you detect something that is designed to be invisible? The answer forces us to get even more creative. We might have to rely solely on its gravitational effects, but push those observations to unprecedented precision. This could mean using the subtle distortions of gravitational lensing, not just to map dark matter's distribution, but to detect the unique ripples caused by individual, asteroid-sized clumps of it moving through the halo of our galaxy. Alternatively, if dark matter does have a tiny coupling to normal matter, it might not reveal itself in nuclear recoils but in other, more subtle ways. Scientists are now designing experiments to look for faint vibrations in networks of precision mirrors or oscillations in magnetic fields that could be caused by a hidden sector dark matter particle passing by. The profound implication of stealth dark matter is that the substance making up most of the matter in the universe might be more alien and exotic than we ever dared imagine. It might not be a simple, solitary particle waiting to be caught, but an entire hidden world operating under its own set of rules, forever beyond our direct perception. Its ghostly nature, its ability to permeate everything while leaving no tangible trace, finds a striking and instructive parallel in a particle we do know, the neutrino. The ghostly nature of dark matter, a substance that might constitute an entire hidden universe of its own, finds a fascinating and instructive parallel in a particle we actually know exists, one that is already famous for its ability to pass through entire planets as if they weren't even there. We now turn to the neutrino, a subatomic whisper from some of the universe's most violent events, and a particle that is itself at the center of a growing and tantalizing behavioral mystery. To understand a neutrino is to understand the concept of ghostliness in physics. These are unimaginably tiny, neutral particles that are produced in vast numbers by nuclear reactions, from the heart of our Sun to the cataclysmic explosions of supernova. Their defining characteristic is that they barely interact with normal matter at all. Trillions of them are passing through your body every second of every day, and over the course of your entire life, statistically maybe one or two will actually collide with an atom in your body. They are the universe's most elusive ghosts, and yet we have learned to catch them. One of the most profound discoveries about neutrinos in recent decades is that they are shape-shifters. They do not exist as a single, static type. Instead, they oscillate, seamlessly morphing between three different flavors as they travel: electron, muon, and tau neutrinos. This bizarre quantum behavior, which earned the scientists who predicted it a Nobel Prize, was a monumental discovery because it proved that neutrinos must have mass, however tiny, a fact not accounted for in the original standard model of particle physics. This oscillation is now a well-established fact, and its patterns are precisely predicted by our models. But now, several experiments are detecting whispers that these ghosts might be doing more than just changing between three known identities. They might be flirting with a fourth, a phantom particle that would be even more ghostly than the rest. This is the hypothesis of the sterile neutrino. Unlike the three known flavors, a sterile neutrino would not interact through the weak nuclear force at all. Its only connection to our known universe would be through gravity, making it a prime candidate for a component of dark matter. The evidence for its existence is not yet conclusive, but it is persistent and compelling. The strongest hints come from experiments like the liquid scintillator neutrino detector at Los Alamos National Laboratory in the 1990s, and more recently, the mini Baryonic experiment at Fermilab. These setups are designed to produce a pure beam of one type of neutrino, and then carefully measure how many arrive at a distant detector as a different type. The data from both experiments consistently show a curious excess of neutrino oscillations, more flavor shifting than the standard three-neutrino model can explain. It's as if you sent out 100 identical letters and, upon arrival, a few of them had inexplicably transformed into a completely unknown language. This anomaly suggests that some of the neutrinos might be briefly oscillating into this hypothetical sterile state before returning to a known one, a process that would throw off the delicate counting. The implications of this reach far beyond the confines of particle accelerators on Earth. Neutrinos are cosmic messengers. When a massive star collapses into a supernova, it releases a tremendous pulse of neutrinos that actually precedes the visible flash of light. These neutrinos carry information about the incredibly dense and violent processes happening in the stellar core, a place we could never otherwise see. If neutrinos have secret properties like the ability to become sterile, it would fundamentally alter our understanding of how energy is transported out of a dying star and how the elements that make up our world are forged in these explosions. Furthermore, sterile neutrinos, if they exist, would have been produced in the hot, dense environment of the Big Bang. They would have influenced how the primordial soup of particles cooled and clumped together to form the first galaxies, leaving an imprint on the large-scale structure of the universe we see today. A confirmed discovery would therefore be a rare and beautiful bridge connecting the impossibly small world of quantum particles to the grandest scales of cosmic evolution. So why do these elusive particles sometimes act in ways that defy our expectations? The answer remains locked away, a secret the universe is reluctant to give up. The data is tantalizing but not yet definitive. Other experiments have failed to see the same anomalous signals, and the possibility of unaccounted for background noise or subtle experimental errors has not been entirely ruled out. Resolving this mystery will require next-generation detectors like the Deep Underground Neutrino experiment, which will shoot a beam of neutrinos 800 miles through the Earth's crust from Fermilab in Illinois to a massive detector in a former gold mine in South Dakota. This incredible baseline will allow for unprecedented precision in measuring these oscillations. The story of the neutrino is a perfect example of how the most insignificant seeming particle can hold the key to monumental questions. Its subtle, anomalous behavior challenges the completeness of our fundamental theories and hints at new physics lurking just beyond our current reach. This quest to measure the subtle properties of fundamental particles finds a surprising and profound connection to our next mystery, which involves not the very small but the very large, the rate at which the entire cosmos is expanding. We have just explored the subtle, ghostly behavior of neutrinos, particles that challenge our understanding of the smallest scales of reality. Now we ascend to perhaps the grandest and most pressing mystery in all of modern cosmology, a fundamental disagreement over the very expansion rate of the entire universe. This isn't a minor quibble over decimal points, it is a full-blown crisis that astronomers have aptly named the Hubble Tension. At its heart is a simple yet profound question: how fast is the universe expanding right now? The fact that we have two different, highly precise methods for answering this question, and that they give stubbornly different answers, suggests that something is deeply wrong with our standard model of the cosmos, potentially pointing toward new physics beyond anything we have ever imagined. The story begins with the pioneering work of Edwin Hubble a century ago, who first discovered that the universe is not static but is continually growing larger, with galaxies rushing away from each other. The speed of this expansion is quantified by the Hubble constant, a number that represents how fast a galaxy appears to be moving away from us for every million parsecs of distance. For decades, astronomers have worked to measure this number with ever-increasing precision. They have developed two primary and seemingly foolproof methods to do so. The first method is a local measurement, a cosmic distance ladder built from the ground up. It starts with incredibly precise parallax measurements from the Gaia satellite to calibrate the distance to nearby stars that pulsate with a known intrinsic brightness called Cepheids variables. These Cepheids are then used to calibrate the distance to even brighter supernova in faraway galaxies. By measuring how fast those distant galaxies are receding from us, a team using the Hubble Space Telescope arrived at a very precise value for the Hubble constant. This is like measuring the expansion of a balloon by carefully watching dots on its surface move apart. The second method takes a completely different approach, looking not at the universe today, but at its ancient infancy. This involves studying the cosmic microwave background, the faint afterglow of the Big Bang, as exquisitely mapped by the Planck satellite. The patterns of tiny temperature fluctuations in this ancient light are a frozen snapshot of the universe when it was only 380,000 years old. These patterns encode the exact proportions of the universe's ingredients: normal matter, dark energy, and the rate at which it was expanding at that time. Using our incredibly well-tested model of cosmic evolution, known as the lambda cold dark matter model, cosmologists can run the clock forward from that infant state to predict what the expansion rate should be today. This is a top-down approach using the blueprint of the early universe to predict the present. Here is where the tension snaps into place. These two methods, each painstakingly refined and each backed by a Nobel Prize, do not agree. The local measurement from the Hubble Space Telescope suggests a faster expansion rate, while the prediction from the Planck satellite's early universe data suggests a slower one. The discrepancy is about 9%, which may not sound like much, but the error bars on each measurement are now so small that the chance this is a simple statistical fluke is less than 1 in a million. It is a real, persistent, and growing problem. This isn't a case of one experiment being right and the other wrong. It is a clear indication that the model we use to connect the early universe to the present day, the lambda-CDM model, is missing something crucial. This crisis has forced cosmologists to consider truly radical solutions. Perhaps dark energy, the mysterious force driving the accelerated expansion, is not a constant as Einstein proposed. Maybe it has been evolving over time, growing stronger or changing its properties in a way that would cause the modern expansion rate to be faster than predicted. Another possibility is that dark matter, the invisible scaffolding of the cosmos, has properties we haven't accounted for, such as an ability to interact with itself or with dark energy in unexpected ways. Some have even proposed the existence of new types of relativistic particles that flooded the early universe and altered its evolution, or that our universe is not perfectly uniform and that vast cosmic structures are subtly influencing the local expansion rate in a way we haven't modeled. Each proposed fix is fascinating, but each one also risks breaking other parts of our cosmological model that work perfectly well. The resolution of the Hubble tension is perhaps the most important goal in cosmology today. It represents a direct confrontation between observation and theory, and its solution will undoubtedly lead to a deeper, more complete understanding of the universe. It forces us to question the most fundamental assumptions about the cosmos, from the nature of its dominant components to the very laws that govern its evolution. This profound disagreement over the universe's current expansion rate naturally leads us to examine another fundamental pillar of our cosmic model: the surprising uniformity of the universe on the largest scales. After wrestling with the precise rate of the universe's expansion, we now pull back to contemplate its most breathtaking and fundamental feature: its overall structure and appearance on the very largest scales. For centuries, a guiding principle of cosmology has been the idea that the universe is homogeneous and isotropic. In simpler terms, this cosmological principle states that if you were to look at the cosmos from any point on a large enough scale, it would appear roughly the same in all directions, a vast, uniform sea of galaxies with no central point or special location. This isn't just a philosophical idea. It's the bedrock upon which almost all of modern cosmology is built, from the equations of general relativity that describe the universe's evolution to our interpretation of the cosmic microwave background. This smoothness is the universe's default setting, its foundational characteristic. the leading theory that explains this remarkable smoothness is cosmic inflation. The idea is that a fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, inflating from a subatomic speck to something much, much larger in an unimaginably short time. This violent stretching would have ironed out any initial wrinkles or irregularities, smoothing the cosmos into the uniform state we observe. It's like taking a crumpled piece of paper and stretching it so dramatically in all directions that any creases become vanishingly small and faint. The theory of inflation is a beautiful and powerful solution, and it is strongly supported by the incredible uniformity of the cosmic microwave background radiation. The temperature of this ancient light is the same in every direction to within 1 part in 100,000, a testament to that early smoothing process. But just when we think we have a handle on this cosmic uniformity, the universe reveals structures so colossal they seem to strain the very principle designed to explain them. Enter the realm of galaxy filaments, the largest known structures in the universe. These are not galaxies or even clusters of galaxies. They are immense, thread-like formations made of thousands of galaxies, vast clouds of gas and dark matter, forming a colossal cosmic web that defines the large-scale architecture of the universe. And the champion of these filaments, the one that truly gives cosmologists pause, is the Hercules Corona Borealis Great Wall. Discovered by mapping gamma-ray bursts which trace the distribution of massive stars across the cosmos, this structure is a mind-numbing 10 billion light-years long. To grasp that scale, if you could travel at the speed of light, it would take you 10 billion years to go from one end to the other. This is a significant fraction of the observable universe itself. The existence of such a structure creates a serious problem. According to our standard models of cosmic evolution, which include inflation and dark matter, there simply hasn't been enough time since the Big Bang for gravity to pull matter together into a structure of this scale. The Great Wall seems to violate a fundamental concept in cosmology known as the cosmological principle, which assumes the universe should look roughly the same everywhere at a large enough scale. A structure this vast challenges the definition of large enough. Is it possible that we are seeing a remnant of a time before inflation, a primordial fluctuation that was so large it wasn't completely smoothed out? Or does it hint at something even more exotic, like a flaw in our understanding of gravity on the largest scales, or the influence of unknown forces in the early universe that could have seeded these gargantuan formations? Surveys like the Sloan Digital Sky Survey have continued to map the cosmos in ever greater detail, and with each new map, they uncover other potential challenges to smoothness, from immense superclusters to puzzlingly large voids. Each discovery pushes the boundaries of what we thought was possible under our standard model. This tension between the overall smoothness of the universe and the presence of these staggering irregularities is a classic cosmic puzzle. It forces us to ask whether the cosmological principle is an absolute truth or merely a very good approximation. It invites us to consider if our universe, on its very largest scales, might have a graininess, a structure, a pattern that we are only just beginning to perceive. The smooth cosmic background is the canvas, but these great walls are the bold, sweeping brushstrokes that suggest the artist's hand was far more complex than we initially believed. As we stand back and survey this incredible collection of cosmic puzzles, a breathtaking pattern begins to emerge. These 21 phenomena are not isolated curiosities. They are interconnected threads in a single, vast tapestry of mystery, each one pulling on the others in ways we are only beginning to comprehend. Consider how the ghostly, unexplained distribution of dark matter seems to whisper to the anomalous rotation of galaxies, both pointing toward a gap in our understanding of gravity itself. The same fundamental force that keeps our feet on the ground appears to behave differently on the grandest scales, and this gravitational enigma might even hold the key to the tiny, persistent nudge that plagued the Pioneer probes on their journey into the void. Look deeper and you'll see how the immense magnetic fields that weave silently through interstellar space could be the hidden engine behind the breathtaking power of fast radio bursts, those millisecond flashes that outshine galaxies. Perhaps the same quantum vacuum fluctuations that leave empty space seething with invisible energy also play a role in the mysterious anomalous microwave emission that complicates our view of the cosmic microwave background. The rogue planets adrift in the darkness and the strange interstellar visitor Oumuamua both speak to a chaotic, dynamic history of planetary formation and ejection, suggesting that our solar system is just one peaceful neighborhood in a galaxy filled with gravitational turmoil. Even the universe's most fundamental settings seem to be in question, with the Hubble Tension revealing a crack in our cosmic model that might be linked to the frustrating search for the universe's missing baryonic matter, two sides of the same accounting error on a universal scale. This grand synthesis reveals a universe that is far more complex, dynamic, and interconnected than the static, predictable cosmos of classical physics. Each individual anomaly is a clue, but together they form a compelling case for a deeper layer of reality governed by physics we have not yet discovered. They are not problems to be solved in isolation, but pieces of a single, magnificent puzzle. Solving the mystery of dark matter could instantly illuminate the nature of gravitational anomalies. Understanding the true source of ultra-high-energy cosmic rays might provide a window into the behavior of particles at energies that unify general relativity and quantum mechanics. The detection of primordial gravitational waves or a confirmed variation in the fundamental constants could revolutionize our entire understanding of the universe's birth and its ultimate fate. This is why the future of exploration is so thrilling. We are not just building bigger telescopes, we are forging new keys for these cosmic locks. The James Webb Space Telescope peers into the atmospheres of distant worlds and the nurseries of the first galaxies, searching for clues to the universe's composition. The upcoming Laser Interferometer Space Antenna will open a new window onto the universe by detecting gravitational waves from merging supermassive black holes, potentially revealing new aspects of gravity. Next-generation neutrino observatories and dark matter detectors will listen ever more closely to the whispers of the cosmos. What all these impossibilities teach us is a profound humility. The universe is not a puzzle we are about to finish. It is an endless frontier of wonder, constantly challenging us to question, to explore, and to imagine. This interconnected web of mysteries shows us that the greatest discovery is not a single answer, but the realization of how much more there is to know. We have traveled together through a gallery of cosmic impossibilities, from fleeting bursts of energy that outshine galaxies to the ghostly tug of dark matter and planets adrift in eternal night. Each of these 21 phenomena is far more than a simple anomaly or a blip in the data. They are profound invitations. They are the universe's way of nudging us, of showing us the limits of our current understanding and daring us to look beyond. These aren't failures of our models. They are the very signposts that have always guided humanity toward its greatest leaps in knowledge. Every time we encounter something that shouldn't be possible, we stand at the precipice of a potential revolution, a paradigm shift that could redefine our place in the cosmos and unveil new layers of physical law we have not yet dreamed of. This journey reminds us that the goal of science is not to accumulate a static set of facts, but to cultivate a perpetual state of wonder and curiosity. It is about embracing the questions more than clinging to the answers. The true value of exploring these mysteries is not just in the eventual solutions, but in the process itself, the collaboration, the innovation of new technologies, and the sheer thrill of the chase. It connects us to every curious soul who has ever looked up at the stars and felt that deep, humbling awe, that insatiable desire to understand the magnificent tapestry of which we are a part. This shared quest for knowledge is one of the most beautiful and defining aspects of our humanity. As we bring this exploration to a close, I want to leave you with the words of the great astronomer Carl Sagan, who perfectly captured this spirit of discovery when he said, "Somewhere, something incredible is waiting to be known." That incredible something is out there right now, hidden in the data from a new telescope, encoded in the path of a distant spacecraft, or waiting to be theorized by a future genius. The cosmos is an endless story, and we have only just begun to read the first few pages. I would love to continue this conversation with you. Let me know in the comments below which of these 21 impossible phenomena captivated your imagination the most. Was it the eerie mystery of Oumuamua, the profound puzzle of the Hubble Tension, or the ghostly nature of dark matter? If this journey into the unknown sparked your curiosity, please consider subscribing to the channel. There are so many more cosmic secrets waiting to be unveiled, and I can't wait to explore them with you next time. Thank you for your time, your wonder, and your company on this incredible voyage. Keep